Thanks, Brian. Has everybody seen my main screen here of the two stream pictures? All right. I'm going to present some data today. I think a lot of people are familiar with the sampling we do with Chester County. It's in cooperation with the Water Resources Authority, and we've been collecting stream quality samples since around 1970. So we have a really long database. Today, I'm going to kind of keep the talk focused on chloride and the chemical sampling we do, but to let you know that we collect invertebrates as part of the biological monitoring program every October, November, early December. And again, this is a program that's been going on since the early 70s. For today, I'm going to focus, I think John Jackson is going to focus on some more of the biological aspect of the chloride. I'm going to focus more on the chemistry that we collect. We have 27 sites that we collect a year. 18 of them are at fixed sites, so we have 1 point a year. These are composite water samples. So we collect at various parts across the stream, composite the samples, and every year we run an analysis for the same constituents. That way we have a nice long database of the same constituents. All of our samples go to our national lab in Denver and have since the beginning of the program. So it's a very consistent collection, very consistent analytical technique. So we have a very solid database on this issue. One thing important with the data I'm going to present, especially the data from the Chester County sampling that we do, all the samples are collected in the October, November timeframe. They're all base flow samples, no storm flow. This is all at low flow conditions. Pretty much it represents a groundwater discharge to the stream. So we avoid any rain events, any snow events, anything that's going on. In the October, November timeframe, we are as far away from salting events as you can get. We're right before the winter season starts. So there's no road salts running into the stream for these samples. So these are all background stream conditions unrelated to any storms, any winter sampling. This graph just shows some various constituents that we do. And I put this up here just to show what kind of the normal pattern in our data looks like. And you can see whether it's potassium or nitrate. We can see year-to-year differences. Again, these data are not flow corrected. However, they are all within a very limited flow pattern, being the low flow sample. So there's not a lot of flow variation at these sites. But you see some ups and downs through the years. There might be a general increase over time, but it generally is a slow increase year over year. There's variation between years, some ups, some downs. So that's kind of a normal pattern of what we see for a lot of the constituents. We tend not to see huge jumps year to year. It's more of a continual slow change, positive or negative. And a lot of sites have little change that go on. However, when we bring up chloride concentrations, we see kind of a different pattern, a much steeper line, a much steeper increase over time. And these are two examples, Valley Creek near Valley Forge and East Branch Chester Creek at Westtown. These are both fairly urbanized areas. They have a lot of roads in their basin. They get a lot of salting in the winter. And you can see at Valley Creek, this is starting in 1998. We have data at some of these that go back, and the trend kind of goes back in time. Notice that the concentrations here, Valley Creek started out in 98, a little bit below 60. It's now running up near 120 to 140. So that's, quite a steep increase that we've seen over time. East Branch Chester Creek, same pattern, starting at around 40. It's up now around 130, 140. So these are dramatic increases that we haven't seen in other parameters. Another thing to note is in a lot of the data, somewhere around 2012, 2013, there seems to be even steeper increase in that line. And this is a pattern that shows up in a lot of sites that we have. In fact, almost all the sites, it seemed to be that sharp increase around 2013. If we look at sites that are in less urban areas, that have less road networks, we still see an increase in the chloride. It's just that the concentrations are lower and the increase is less. So we're seeing concentrations. This is Big Elk Creek near Maple Grove, and we're seeing around 20 up to maybe about 35. So it's a significant increase, but it's not the increase that we've seen in more urban sites. Octorara Creek, same situation where we're seeing a definite increase from maybe in the 17, 18 range up to around 25. But we're not seeing that sharp spike. But also, if you notice in these around 2013, 2014, that line seems to get steeper. Seems to be something that happened around then that's increasing the chloride concentrations. At some sites that are a little bit mixed, West Branch Brandywine, East Branch Brandywine, they tend to start headwaters in agricultural forested areas, then run through urban centers. Again, the pattern's the same, where we're seeing chlorides increase from the 2030 range up to the 50-60 range. So this has been consistent at every site that we have long-term data in. There's been an increase. The more urban, the more roads in the network, the faster and the bigger the increase is. Just for some background, this is a graph of Baptism Creek, which is up in French Creek State Park. Very few roads cross the stream. There's very little inputs, and we're getting background chloride concentration in the 2 to 3 range. Now, chloride can change based on geology, based on inputs, but most of the streams we have are starting out in at least the 20 to 30 range, which is well above probably the natural background for these streams. And many of them are now approaching 60 to 80 milligrams per liter of chloride, which is significantly higher than they've ever been. Looking at some data from 98 to 2009 from an old report we had, there's a definite sharp relationship between the percent of urban land use and dissolved chloride concentrations. Obviously, the more urban land use we have, the more chloride we're getting. A very strong relationship there. This is a graph that Chester County put together with our data, and it just shows that same pattern. This is results from the 2018 sampling that we did. And you can see that the highest values we have are in the more urban areas. So the Delaware Basin, kind of along the Route 3 corridor, heavy urbanization, lots of corporate centers, lots of shopping centers, parking lots, roads. We get higher chlorides. Valley Creek, even French Creek or Pickering Creek in Phoenixville, after it's picking up a lot more. You see our lowest values, the headwaters of the Brandywine, Pigeon Creeks, areas that have a less dense road network. So there's a different relationship between the urban environment and the amount of chloride we're getting in the samples. You can see even down at Red Clay, we're getting up in the 60-80 range, where upstream of there, we're in the 30s. These are a couple sites that we have that long-term data we've been collecting since the 70s. And you can see back in the early 70s, we were down in the 10-20 range. French Creek's on the bottom here, and you can see a very slow rise. It has risen, but kind of not as sharply, where the more urbanized basins of Valley Creek and East Branch Chester Creek, there was a slow rise up into the 90s. And then as we hit 98, that rise seems to increase. And then when we get to that 2013, 2012 time, it's gotten even higher. So for some of these sites, they were down maybe 25 in the early 70s, and they're now running up near 150. So that is a very significant rise for a constituent over time. I mentioned before that these are stream water samples that are mostly groundwater oriented. I did pull some data on some groundwater wells we have and found 2 examples. We don't have quite the long-term data, a lot of these groundwater wells, a lot of point samples over time. But one well, CH1567, was a well that NACWA had sampled. So there were multiple samples from 1999 to 2019, actually 2021. And you see the same pattern. Started out in the 40s, raised up to around 60, and then in that, somewhere in this, now we don't have quite as many points in here, but somewhere between 2013 and 2021, a very large increase in groundwater. Well, at CH10 that we don't have the long term. This one is part of the Pennsylvania Groundwater Network we're running, and it's going to be sampled every year. It just started in 2018, but you can see for those couple of years, there's been no change really. And this one is a much more rural area down near Doe Run, not as many roads, a lot of pasture land, so we're not seeing quite the influence. So it's definitely, the groundwater is also being inundated with salt at this point. One thing we do keep track of, we have a lot of gauges that have specific conductance real time being measured. This is a graph from Modena on the West Branch of the Brandywine. And the general pattern is in the summer, spring, and fall, when we get rain, generally as discharge goes up, you'll see conductance go down as that fresh rainwater washes in. It's low in conductance and the conductance will drop. However, in the winter, when there's salting events, we see the opposite of that. And what these peaks represent are, these are salting events in the winter. This was last February. And you're seeing spikes in conductance going from around 420 up to over 1,000 several times. So these are events when there's salt water running into the streams off of the roads, and you can see these peaks. We collected some samples this fall, and we have a monitor running at Cobbs Creek in Philadelphia. So this is a very, very heavy urbanized area right in the middle of Philadelphia. And we're seeing conductance peaks that are going up over 6,000, 4,000 regularly in the winter when there's runoff events. So these are very high concentration events that are hitting the streams. You can see after the event, we're back down. It normally runs 600 or 700. So these events are short term, but they're very high concentrations of chloride. We did collect some actual chloride samples to go with some of these samples also last winter. So give you an idea, in Frankfort Creek in Philadelphia, several different storms of different magnitudes, but we got somewhere between chloride milligrams per liter of 130 and over 1,000 milligrams per liter in one sample. Darby Creek, same storms, we got between around 100 and 650. So these are very high concentrated events. They may be short-lived, but they do happen every time there's a salting. One thing we're working on with Chester County too is that we have several sites, the Brandywine at Chadds Ford, Valley Creek near Valley Forge, and White Clay Creek, where we're going to be producing conductance chloride surrogate models. So it will give you kind of a real-time chloride value as long as the conductance monitor is running. So they will be coming out shortly and will be available on our website. It'll be a way to get kind of real-time chloride information for those sites. Just to let you know, this is a graph from some Wisconsin USGS data. This is not a problem that's unique to southeastern Pennsylvania. This is a problem that has been seen across all the areas in the country that receive salt in the winter. Data here, you can see the same pattern where this is showing summer, spring, winter, and fall. The winter is obviously higher, but you can see theirs happened around 1995. There seemed to be this rise in chloride that happened in the winter, all seasons. So that seems to be a pattern that we've seen more like 2012, 2013. Looks like Wisconsin was seeing it maybe a good 10 years earlier than that. So just a quick summary is the chloride concentrations have gone up 2 to 3 times since 1998. So it's a significant high rise. And keep in mind that these rises have occurred at this was data that was in the fall. So this is not related to direct storms. This is groundwater input that is slowly released through the year. And the higher chloride concentrations are associated with higher urbanization in the watershed. The more roads you have, the more parking lots you have, the more chloride we're getting in the streams. Now that rate of chloride increase can't be explained simply by there being more roads, because the amount of road increase and parking lot increases has not doubled or tripled in the last 20 years. So there seems to be either a buildup in the baseline concentrations or some kind of increase in salting or number of events. Something has changed that's causing those chlorides to increase quicker. It may be that the groundwater is just becoming saturated. More and more salt is going into the groundwater. Base flow samples are below the EPA chronic water criteria of 230, but storm concentrations can easily, as you see, exceed that multiple times throughout the winter. We're going to be trying to operate as many conductance monitors as we can through the winter and trying to develop as many of these chloride to conductance surrogate models and try to keep them running so we get some idea of what the maximum chloride concentrations are in the winter are. So that's what we're working on now. If we have any questions, I guess we can hold them until John presents his maybe. Brian, I think that might be the best.
Yeah, I think that's a good thing. And if you want to save them in the chat, that's a good place to put them as a holding place, or we'll open up the microphone. So thank you, Drew. Very thorough. Appreciate your work on pulling all that data together and some of the newer information. So now we'll switch to John Jackson with Stroud Water Research Center. John, go ahead and share the screen. Thank you for your time, John, putting your presentation together. John, we're seeing a portion of your screen. You're also muted. It's about a fifth of this. There we go. That's good. So if you're just joining us, saw a few people sign in. This is a second presentation with John Jackson. Drew Reif just presented his data. We are recording this meeting, so it will be available on our CWMP YouTube site. If you missed Drew's presentation, you can see that.
Gosh, I'm trying to turn presenter view off. I'm open to suggestions. How do I turn presenter view off?
Yeah.
What I see.
You're seeing all that?
Yeah.
All right, so that's it's messing around with.
Oh. Funny, it looks like when you close out of it, we get a full screen for a flash second and then it's gone.
All right. How about we try this? How's that look for you, Brian?
Looks good, John.
So,
Looks good.
title of my presentation today is both optimistic and pessimistic, because as Drew just showed you, we have salt everywhere. And the real question is, does it matter? And where and when and why? So there's going to be a lot of information, and I'm sorry, I'm going to go fast, but there's a range of things you need to think about. So here's my take-home messages. We'll start with them. This is a contaminant at this point. Road salt, sodium chloride is appearing in our waterways at such a level we have to be concerned. And it's not one that's tightly regulated yet. This was not an issue when the Clean Water Act was passed. It wasn't an issue like Drew showed you in 1970 or 1980, but it is one now. And the states and the regulators are struggling to catch up. Salt toxicity based on bioassays depends on the type of stream, the duration of the exposure, the water temperature. All important issues, as you saw in Drew's presentation. The increase in salt use reflects concerns about safety, the economics of winter storms, and then societal and political concerns and priorities. This is not something that happened. It's something we ask for and we pay for. And finally, there's now increased concern about salt use, but the increase itself didn't really pay attention to the health issues, the infrastructure issues, or even the environmental impacts. And so the conversation is changing now as the issue becomes a bit more of a hot topic. So when we call it an emerging contaminant, or a contaminant of emerging concern, it just means we need more information. And quite often we hear it referred to for pharmaceuticals in our water, personal care products, antibiotics, steroids, bactericides, pesticides, and lately PFAS, the forever chemicals. These are things that you hear a lot about as being a contaminant concern. But there's lots of roadway pollutants that we're starting to pay attention to, whether it's de-icing salts or PAHs and seal coats, or most recently, a tire chemical that's found to be quite toxic to salmonids. This is a relatively new thing. We know that urban streams struggle to be healthy, and one of the reasons is probably these emerging pollutants. We just don't know much about them. But we do know a fair bit about salt. We live salty lives, and therefore we know a fair bit about what we're using and where we're using it and how we're using it. And one way we're using it is in road salt. So this is a graph for the United States that shows road salt use beginning in 1940. This graph ends in 2005. You see a gradual increase leveling off around the 70s and staying consistent until the mid-90s, and then these giant spikes in the mid-90s. Now we're at 23 or 24 million metric tons of salt per year, road salt use in the United States. So we've gone up again, and this pattern parallels the data that Drew just showed you. The spike here, and now another spike up. But what it means is our regulations, which came into effect, say, in the early 70s, weren't looking at a problem because the water that we were sampling was water that, for example, went into the ground 20, 30, 40 years earlier. Now we're sampling water that's receiving a lot more salt and has for decades. The concern, or the first paper I'm aware of, is actually from the Philadelphia area. And this was done from the water intake data for Philadelphia out of the Schuylkill. And these are the data, they published it in 2003, but it looked at data from 77 to 1999, and chloride doubled and sodium chloride, or sodium doubled in that time period. And this was the first, for me as a scientist, the first red flag that we have salt problems. Since then, numerous papers have been published. You can now produce a map for the entire nation where these red areas are areas where salt has increased dramatically. All of the yellow areas are areas where salt has increased measurably. Much of this is due to road salt, but not all of it. In some areas, it's about water softeners, especially in the Midwest, because they have such hard water and you use salt as part of the softening process. This is a map, and I toss this in here. First of all, reemphasizes 24 million tons of salt a year, emphasizes the salt belt up here in the north, in the northeast, in the mid-Atlantic, but also all this gray area in the west, they're using a mix of sand and salt. The only place that's really salt-free tends to be in the south. And so we're seeing increases in salt in streams, in lakes, in rivers, in wetlands, in groundwater. It's showing up everywhere. And the last thing I'll note is this map was put together by a company that was paying attention to corrosion on tractor trailers. Drew mentioned this, and I'm going to use some local Chester County data to emphasize it, that the salt concentrations in the streams where it's elevated is always elevated. And this is especially true in our urban streams. These are some data that Patty Hay, who was a Westchester Master's student and also a Chester County Master Watershed Steward, collected. These are 5 tributaries draining from Westchester Borough. They were only picked because it was an opportunity. Westchester, the borough, is kind of on a hill, and there's 5 different tributaries draining away from them. This is a single sample. Late summer, again, just like Drew, this is September. So no storms anywhere near these. Notice the range of values from 0, this is conductivity, to 1600. This is much higher than the data Drew was showing you. And the chloride is topping out over 400 in this set of data, as opposed to what Drew was showing you, which were conductivities in the, maxing out more in the 400 to 500, and chlorides maxing out in the 100 to 150. This is just background groundwater, because all stream water at base flow is really groundwater coming to the surface. So it's Plum Run, it's Black Horse Run, Taylor Run, Goose Creek, which is a tributary to Chester. So all the first 4 are all tributaries to the Brandywine. The last one is to Chester Creek. For a reference point, the White Clay Creek at the Stroud Center, we average about 12. So it's not pristine. That's because of agricultural, but gives you an idea of the difference. 300 years of agriculture in the White Clay Creek upper watershed here has elevated our salt load from, say, 5 or 4 or 3 up to 10 to 15, averaging around 12. This is the chronic EPA standard. What they define that as is a 4-day exposure once per year, one time every 3 years. We're seeing that at 2 of these sites being surpassed every day in August, September, October. So we're well past what EPA considered a chronic toxic load in at least 2, if not more, of these streams. And that's a base flow. And like Drew said, this can also be very variable. This is down on the Brandywine in Delaware, just outside of the Concord Mall area. So downstream of 202, it's actually in First State National Park. We see much higher conductivities again than Drew measured. Instead of peaking at 5,000, these sites around Westchester, Plum Run around Westchester, as well as Rocky Run, peaks out in the 40,000 to 50,000. This is a 4-day running average, peaking out at 25,000. Seawater is at 55,000. So both of these streams have approached seawater at least once in the last 3 years. So what does it mean? So we've run some tests for Pennsylvania DEP and for DRBC, Delaware River Basin Commission, that are toxicity tests. And I'm going to report to you what we refer to as a LC50, the lethal concentration that kills 50% of these bugs that we're working with. And that's what we're working with, our mayflies. So this is a dose response curve where at a low dose, everybody survives. And as you increase the dose, eventually you start killing insects. And the LC50 is that concentration, in this case, this illustration, just under 4,000, where 50% of your individuals die. It's a simple way of reporting toxicity, and it's a way of comparing across toxins as well as across taxa. We've looked at, asked the question, does the age of the animal matter? Does the duration of the exposure matter? Does stream type matter? Hard versus soft? Does the species involved matter? And finally, does water temperature matter? Fact is, all of them matter. In every test we ran, younger mattered, duration mattered. But the 3 most important were how long the test ran, what type of stream water, hard versus soft, and what was the water temperature. So let's walk through those 3. Duration of exposure, we ran 2 tests. One is a 2-day test, so like a spike. And then the other one was a 30-day test, which would be closer to your base flow. And what we found is the longer the exposure, the more toxic the chloride. So the LC50, when we went to the longer exposure, was 1/4 of what you would find for an acute test. So the longer the exposure, the less salt they will tolerate. Toxicity increases as exposure increases. Hardness varies greatly, both within Pennsylvania and across the United States. Our hardest water is in the montane and middle America. Our softest water tends to be, for example, in the coastal plain and Piedmont of the eastern portions of the United States. That includes Pennsylvania. What doesn't show up in this area, being in the Ridge and Valley, is these little limestone streams, which can be very hard in and amongst a bunch of watersheds that are not very hard. We found that hardness made a big difference. We sampled water that went from White Clay Creek, which would be considered moderately hard, to Dyeberry, which is in the upper Delaware, to Spruce, which is in the upper Susquehanna, which would be considered quite soft. The harder the water, the more salt they could tolerate. That was the bottom line. So in this case, there was an advantage to be in a hard water system. But remember, for most of Pennsylvania, most of the mid-Atlantic, relative to the Midwest, all of our streams tend to be soft to moderately hard. Finally, temperature. You know, salt is out there year-round. So what's the difference between winter versus summer? So we ran tests comparing the toxicity at warm summer temperatures, which were going to be in the 20 to 25 degrees C. And this is what you would see in streams around here in July, August. And then we did our best to get to winter temperatures. We took it down to 5, just above freezing. It's very hard to drive it lower than that because you start getting icing in the lab apparatus, and that blows everything up. Bottom line is, as you warm it up, the toxicity increases. That's to be expected, but we needed to demonstrate. The good news on that, it means that to some degrees, those higher winter concentrations may be less toxic than actually the warm weather concentrations that we observe in July, August, September. That's going to come into play eventually. It hasn't yet, but my suspicion is there's going to be winter criteria and summer criteria, and the reason why is average lab temperatures for toxicity testing are 20 degrees. That's just standard, 20 or 25. But this is again the conductivity graph for the Upper Rocky Run down in Delaware. If we use that criteria, there were 21 days in this little period here in 2017 that would have violated that criterion. If we use a winter criterion, then there's only 2. That's a big difference. 10 times as many days violating a 4-day running average. And so as a regulator, they're going to do their best to be applicable, and temperatures might be one that they're going to try to incorporate. To my knowledge, no state has done it. This is very new science. So in the end, what our studies told us is the duration exposure matters a lot. The stream type, water hardness matters a lot, and water temperature matters a lot. The one test we didn't run was comparing the different kinds of salts that are used as de-icing salts. Everything we did was with sodium chloride. So these are some data that EPA has paid for by various people. And these studies actually date all the way back into the 70s. They started doing work like this. What they've found, and these data illustrated, is of all the salts we use, sodium chloride is probably the most benign, whereas magnesium chloride is the most toxic. And the more they do this work, the more I'm convinced that the conversation right now and all my data is translated to chlorides. But it's actually the thing that matters is probably going to be whether it was sodium, magnesium, or calcium chloride when it was applied. But so these are LC50s, and you notice the lowest values in all 3. So Ceratophrys and Daphne are standard lab animals, zooplankton, and this is a fathead minnow, so it's a fish. This was the most toxic of the salts that we looked at. So why has it increased? Drew posed this, and here's my hypothesis. It's impossible to find any explanation on why we're applying double or triple or quadruple the amount of salt that was applied in the 70s when I was a kid, or when my parents were adults and making these choices. It seems as though road safety, economics, expectations, the public expectations, and politics all come into bear in these increases. One of the important factors I think that resulted in that mid-90s spike was a couple of studies that looked at road safety and suggested that salting reduced accidents. It's a very limited study in both cases, and one of the things that doesn't get corrected for is whether travel velocities increased and whether that you actually end up over the long term with equal number of accidents. They just change the driving behavior. But these studies show that once they started salting, accidents in the hours after salting went down. There's an economic argument. The quote I pulled, salt applications pay for themselves within an hour. Winter storms, you're late for work, you may miss work, slower travel, transportation is impaired, reduced productivity because people are not at work, schools closed, people need to stay home. There's an estimate floating around that a single winter storm results in, on average, $2.9 billion in cost associated with the storm. So by doing a little magic of chemistry, we can save the economy a lot of money. That's the argument. The third thing, expectations for clear roads and politics are linked. This is especially true for those of you who remember the 1990s around here, where the fate of many politicians was determined by how they responded to some big storms in the 90s. So originally, when I grew up, we talked about roads being passable. Was it passable? Versus now an expectation for the road to be clear. And the complaints are registered with the municipalities or with the state when the roads are not clear, not just a matter of passable, but clear. Then there became expectations and loss of convenience when it wasn't perfectly clear, and that went to the voting box. In other words, politicians paid a price if they didn't have the roads looking clear as could be in the middle of the worst storm of the year. As all that was happening, though, we've seen a slow increase in the negative impacts, the concerns around increased salt in our waterways. There's been conversations about taste and health, conversations about infrastructure costs, and conversations about aquatic toxicities. At this point, it's well enough known that this whole pattern is now referred to as the freshwater salinization syndrome. This is not a Pennsylvania issue. It's not a Christina Basin issue. This is a worldwide issue, and it's especially important in areas where road salts have been used at this point intensively for 50 or more years. So let's walk through it. Drinking water, one of the concerns is lead. That's what PB is. Most people don't realize that much of the conversation about lead in the Flint River, in the Flint water plant drinking water issue was tied to switching to a water source that had elevated salts due to road salt use. There's concerns about sodium. I put up here a study that was done in New York. They sampled almost 1,000 wells, and this is just a heat map where green is low sodium concentrations and orange, yellow, white, orange, red, and white end up being high concentrations. 50% of these wells exceeded the low sodium criteria for drinking water. The low sodium, if you were on a restricted sodium diet, 50% of these wells had greater than 20 milligrams per liter sodium. 10% exceeded the drinking water case standard of 250 milligrams per liter chloride. 10% of the wells. So it's suddenly this groundwater contamination becomes a drinking water contamination problem. Infrastructure and damage is really something that I thought we had forgotten about. I grew up watching cars rust away, and we seem to have solved it. But now it's back. It's obvious, and it's costing us billions. It's true for public property as well as private property. And if you haven't noticed it, next time you're walking through the parking lot, take a look at cars that are now showing salt damage, rust around their wheel wells, something that was really prominent in the 70s, but not so much in the decades after. I found two estimates of the cost. One is from Montreal. This is this gray slide here, and the other is out of New York. A couple of take homes. These are both busy. For the Montreal study, they estimated that if you're spending $100 per ton of road salt, your infrastructure costs are going to be $600. Your vehicular damage are going to be over $100. So $100 of road salt is buying $700 in infrastructure and property damage. The New York study looked at it slightly differently. They included ecological impacts, but it was really relatively insignificant compared to infrastructure and vehicles. Bottom line for them, they estimated that road salt use up there was costing about $25,000 per lane mile per year. It's something we haven't talked about, but people who are tracking this, whether it's road engineers or people chasing the money, are starting to pay attention and moving aggressively to try to control this. So how do we do it? It really, the conversation can't be safety and economy versus streams and infrastructure and drinking water. It can't be either or. It really needs to be all at once. The answer to this question, the parts of this puzzle, are going to have to be balancing all of these concerns. What's that mean around here? Well, I did a quick back of the envelope estimate for what it means for Pennsylvania. My best guess is PennDOT is applying about 150 pounds per person per year. Municipalities based on work in the Midwest are probably equaling that. So another 150 pounds per person per year. Private applicators, this would be homeowners, but probably more than that. This would be private parking lots, private roads, are probably applying about 100 pounds per year. Based on these estimates, that's about 400 pounds per person per year. That was back of the envelope. I later found that the state of Michigan estimated that for Michigan, that's the number they estimate per person per year for Michigan. So that's a ballpark figure. It's not a bad one in terms of guessing. But if you figure per household, there's 3 people in a household, you're suddenly up to 1,200 pounds per person per year. And if you take 2 households, 6 people, then you're almost at 1 pallet, 48 bags of 50-pound salt per 2 households per year. Think about a truck pulling up in every other house, putting a pallet of salt down and saying, this is your allocation for the year. That's what we're doing. So if you're wondering about why we have a problem, think about it in those terms. Well, most of that ends up in the waterway. So I took the conductivity meter at the USGS that Drew was talking about. That's right by the Brandywine River Museum. So these are data for the Brandywine. And I took their chloride concentrations and I just multiplied them together. This doesn't include a bunch of winter storms or anything. And it suggests to me that there's 37,000 tons of sodium chloride, salt, flowing by the Brandywine River Museum in the Brandywine every year. That's 80 pallets of salt per day. And that's not one of our bad sites. That's just what's going on. But remember, at 400 pounds per person, that's per year, that kind of makes sense. So how do we reduce it? The suggestions are out there, come from a variety of people, but basically I translate them. We're going to need more muscle and more machines. We're going to need to be calibrated in our chats. We're going to have to rely on friction and traction more than salt, more than chemistry. And we're going to have to address what's reasonable expectations for travel during winter storms. And the last one is one that's probably outside of our wheelhouse, but at a certain point, I think the whole process is going to benefit from a certification program. So let's walk through, what do I mean by more muscle and machines? It's about shoveling and blowing and removing the snow physically, both for the homeowner as well as for the municipalities or the landowner. The other thing that goes along with this is the use of brines. Believe it or not, Maryland has cut Maryland DOT has cut their salt use in half. And one of the ways is by aggressively brining. They actually apply brine behind the plow versus applying road salt. And the reason why is this brine goes right to the surface and doesn't get removed the next time the plow goes by. 50% reduction. Thank you, Scott Ensign, for linking me to that data point this morning. The other thing is about calibrated. You know, people want to see the salt, and we're applying way more than is recommended. This is an illustration out of Toronto, where this is the recommended salt application, 20 grams per square meter. This is the typical parking lot application, which is 7 times greater. We're applying a lot more salt than the maintenance people, the maintenance science would say we need to do. And it gets calibrated by temperature, the type of precipitation, and the type of traffic that's going to be occurring. There's a lot of recommendations out there. And the challenge for the municipality is even having the ability to calibrate their application rates. But that's the only way we're going to control it. And that's true for parking lot maintenance too. Friction and traction, snow tires and anti-skid aggregates, in other words, sanding. I did a presentation a few years ago to the conservation districts of Pennsylvania, so 150 people in the room. Asked them how many of them had bought snow tires, and a fraction of them had raised their hand. Then I asked them, how many of you bought snow tires in the last 5 years? Not one. Nobody is buying the tires. They're expecting the road to be clear enough that they don't need snow tires. But it's also about expectations. I grew up out in the West, in the mountains of Colorado, where you had chain laws and you had storm speed limits that were significantly less. The idea that there's an expectation that you can travel at 50 or 60 or 70 miles an hour and you will complain if you can't in the middle of a blizzard is just a false expectation. The road cannot be a runway or a speedway in the winter. And the law needs to help reinforce that, slowing down, having that expectation that people are going to travel slower. It's safer. And it also means that our expectations on road maintenance are different. Finally, certification programs. New Hampshire has one, Minnesota has one, Madison, Wisconsin has one. These can go a long ways to helping the municipalities, helping the private landowners do the right thing. There can be trainings, but it's different when it's certified. It's different when there's liability insurances tied to it, things like that. So points to remember, we have a salt problem. It's new. It's not something we knew about in the 70s. It's not that salt is a problem everywhere. It's increasing everywhere. But most streams right now are not at a problem level. However, we are seeing some sites where it's clearly lethal concentrations are present already. That depends though on the type of stream, the duration of the exposure, water temperature, but the laboratory data and the field data together say we've got salt impairments that right now are unrecognized. Fourth thing, the increase in salt represents the best of intentions, safety and economy. And it was asked for and paid for by us. So there's no one to blame, but we created another problem in the process. Now the negative impacts of increased salt use, they're not going to be easily resolved. And the reason why is we're addicted to road salt and what road salt allows us to do in the winter. And until we change those expectations, it's going to be very challenging to reduce our salt load. But that being said, there are examples out of New York, out of Colorado, now out of Maryland, where road salts have been significantly reduced, 30 to 50%, without any loss, to my knowledge at least, significant decline in winter travel conditions, just much better, much more judicious use of salt. So that's all I have, Drew.